Chris Bissell and Yadid Ramot and Jeremy Custenborder from MySpace. Please give them a round of applause.
Thank you. Thank you very much. Got to find the power plug here. It's on the left. There we go.
You guys have been rocking this thing out.
We're doing a really technological presentation. We need the Elmo to be up first. Huh? Oh, it's up? Okay. Is it upside up? Awesome. Oh, and I can see it. Beautiful. Okay. Thank you, everyone, for your patience. This is, tracking performance at myspace.com. Obviously, tracking performance at myspace.com involves millions of things, millions of topics. We're going to talk about a particular subset, a particular challenge that we've had over the years. Last night we went over, in Spike Night, and we're going to go over some of this again. In Spike Night, we went over a bunch of the tools that we use to monitor performance in production. Production is a big deal. We have over 10,000 servers. We have lots of different VIPs, hundreds of databases, hundreds of middle-tier servers. Everything is incredibly complex. The problem there, of course, is that in the end, the site itself is developed on someone's workstation. Someone's workstation does not replicate a production environment in which there's thousands of servers talking to thousands of servers. What we've found, I'm going to transition slides right now with my clicker. What we found in general is that, yes, production environment is more complex than the development environment. We've also found that oftentimes load testing works too late in the game when it comes to giving feedback back to developers who are iterating on their feature. We've also found, and I'm sure this is sort of a truism of software development, is that fixing problems once they're in production is very inefficient, almost as inefficient as my spelling. Fortunately, we have a word for Elmo, so this is good. So what we're going to go over in this presentation is we're going to do a quick architectural overview of the site in general, just to give you a sense of what's talking to what. And then we're going to go over 3 problems that we've encountered over the years, 3 actual scenarios. And then we're going to talk about a particular system that we developed in order to give developers more feedback on the day-to-day about how their code will operate in a distributed environment in production. And at that point, we'll take questions, because I know a lot of you are building those kinds of tools. We want to hear about them. We love to hear about them, because this is an unsolved problem. The stuff we're talking about is not solved. It is our humble and desperate attempt to solve those problems. So, thanks to Mr. Elmo. Somebody stole my pen, by the way.
Chris.
Huh? Oh, there it is. Okay. Sweet. All right, so MySpace architecture 101. We're going to spend a couple minutes doing this, and bear with me, ask questions as we go. The first thing we do in the MySpace architecture is we store data. So in the top left here, I'll draw our databases. We like to do this in analog so that we can actually have a sort of narrative format as we draw them, so you don't get overwhelmed by the whole system as it's shown in one piece. We shard our databases. We actually federate them through a range partition that was talked about several times at this conference. We partition our users by million range. So a particular database will hold 1 million users. So we got 0 to 1, 1 to 2, 2 to 3, X. At the time, we have 400-something of these guys. We've ramped up a lot of users over the years. We've also ramped up some spammers, as people probably know. So these are federated databases. They store atomic user data. They store all the data that is particular to one user. So that way, when we're painting someone's profile, we have one target out there in the middle tier for the web server to grab all of its information from. As has also been talked about in this conference and in many blogs, the first thing you encounter when you partition your data, besides crying, which we cried a lot, and we still cry, we continue to lament our inability to have a nice RDBMS in front of everything, is that you end up having to make distributed queries against these guys when you need to put aggregate data together. For example, we store a user's blogs on their particular database against their user range, but what happens when we need the top blogs on the site? So that's our other particular type of data store, which is, we call these our feature databases. These databases tend to store an entire stack of data, an entire vertical stack. Databases are pretty scalable when it comes to large vertical stacks of data, as long as you don't do nasty things like store n-size text fields and stuff like that. So we have certain feature databases. Examples of these would be, databases that store aggregate blog information, databases that store aggregate video information, and such. As you know, the first thing that you encounter as a scalability problem when you have databases is the fact that even though you've partitioned them heavily, you still have a single point of failure on a database. And there's certain options that you have there, such as clustering, replication, etc. In our case, we have too many databases to be really cost efficient for sort of fully redundant replication. So we put a caching layer in front of those databases. So I'm going to draw a cloud here. The system we built for our middle tier caching is called Data Relay. Data Relay is it's a problem that people like to solve in these types of environments. It's a generic system for doing clustering, replication, and messaging. So Data Relay gives you a nice coding environment in which you can write storage components, and it takes care of the act of talking between servers and the act of having web servers talk to these servers. So examples of the things we do with Data Relay are key value storage, which is sort of the engine behind social networks and many other scalable websites. So we have key value stores. And we actually have several of these, but for this diagram, I'm going to just show it as one sort of generic key value blob. And then we have other components that we can push into Data Relay as well. For example, in the key value stores, we use Berkeley DB as the backend. That comes with the benefits. This was also at another talk. The benefits are a very mature and stable code base. We're looking at other options right now, like Tokyo Cabinet and things like that. But Berkeley DB is doing pretty well for us right now. And then we have other types of stores that are built on the relay system. For example, we have counter store. I'm just going to burn through some of these. We have counter store, which stores counters that can roll over 1 + 1 + 1 + 1. We use this for profile hit counters, video counters, etc. And then we have another system called index store. And index store stores things in many-to-many relations. It stores, there's one tier of servers that stores the index. There's another tier that stores the values. This solves the problem that we encounter many times as a social network, where we have things that involve looking at data through the lens of your friends. For example, we have the bulletin system, in which the UI that we present to the end user is a list of the bulletins their friends have posted, counter-sorted by the last date of that post. In order to put that data together, you have to take the entire user's friends list and join it onto all the bulletins that have been posted on the site within X period of time. Another system that uses that is activities, which is, people have done something, we post it into a generic system. All that happens through index store. So all of these systems are talked to by a variety of tiers of servers. In some cases, we have a system called prepopulator. Prepopulator is a pluggable system that knows how to talk to the databases and push the data into the caching layer. So in some cases, prepopulator will pull data out of the databases and push them into something like index store, where we get a lot of benefit from storing an entire index in memory so that we can traverse it tens of thousands of times per second, which is how often we have to do that. So another data storage component we have is called Transaction Manager, which is all these things are built on the relay system. So Transaction Manager is a system where you can put together what we call a transaction, which is actually a list of work items, doing work against SQL, doing work against data relay, doing work against index store. The web servers will put together packages of work and push them into Transaction Manager, which then treats them as a persistent asynchronous queuing mechanism. So it will push the data into these various systems with all of the concurrency issues that you might imagine. There's a whole conversation we can have about concurrency in these types of systems. And now I'm going to draw the part that we actually encounter on a day-to-day basis when we're writing our web code. And that's the focus of this talk, is the act of a developer writing a feature for MySpace or for any large site, in which the training you typically get is you build a website against a relational database. There's so many wonderful persistence frameworks for rapidly developing an application in that environment. And unfortunately, we have to dismantle a lot of those pieces to scale a site like MySpace. The moment you do a join, that becomes problematic at MySpace. I'm sure there's up-and-coming products out there that solve this problem, but it's a tricky one. So I'm now going to draw our web farms, and then the last and probably most topical piece of scalability at the end. So we tend to partition our front-end functionality by its middle-tier dependencies. So each one of these clouds is a web farm. I'm going to draw a lot of web servers. And these servers host our web code and the client code for our APIs that actually encounter the middle tier. So this one, for example, would be, we tend to partition by VIP, by subdomain. So this will be profile.myspace.com would be one farm of servers. This would be messaging, which is actually mail.myspace.com, which is our mail system. And another example of this would actually be a totally separate thing. We have our mobile site, which hosts a different set of web code but uses the same APIs. And then finally, we have the end user. So the end user is hopefully happy. They're not happy if we don't scale. This is their browser. And one of the points we want to make in this diagram, because it's a very topical point at this conference, is the fact that all these thousands of servers converge on the browser. I'm trying to point at it using the monitor. And then here's the interwebs. Between the browser and the servers, we have our load balancers, netscalers. And we use those guys to protect the web servers from excessive amounts of traffic, from excessive numbers of multi-latency connections, everything that load balancers are very good at doing. And so ultimately, the browser will resolve and connect to a load balancer, which ultimately will resolve and connect to a web server, which ultimately will resolve and connect to any one of several key value stores, any one of several counter stores, and any one of several index stores. This is where things start to get complicated. This is where it becomes difficult as you're writing code that works on the front end to know what middle tier system you're dealing with. In our code base, that is obfuscated in the sense that we build an API layer that masks a lot of the persistence logic so that people don't have to worry too much. The problem, of course, is that there are enough problems in a complex production environment that, at least in our case, and I'm happy to hear about how we can fix this, people still have to worry about these issues. We have concurrency issues, we have dependency issues, we have versioning issues, everything that comes out of having thousands of servers talking to thousands of servers. So when it comes to bottlenecks, we can actually reduce these to a couple of basic bottlenecks. And we're going to talk about, go over some real-world scenarios that actually show how these bottlenecks manifest. You have I/O bottlenecks, which is web server I/O against middle tier. You have web server bottlenecks, which is web server memory allocation, etc. And then you have browser bottlenecks. And this is our topical topic. Thanks, Mr. Souders. Browser, all about CPU, memory, etc. So without further ado, we're going to start transition into our non-Elmo part of the presentation. So, how do I do that? Oh, they did it? Oh, sweet. Okay. I'm one of those people who should really not touch technology. This is an operations conference, and Jeremy here is one of our super lead operations guys, and I'm one of those really irritating developers who just thinks of it as the cloud. This is the same laptop that we used yesterday, by the way. Did it go to sleep? Huh? Oh, okay. It's one of those fun things. Okay. So we're going to go over 3 problems that we encountered in the past. We will have no more problems in the future because we built a tool to address it. So sorry, guys. We will have no more problems. And we're going to talk about how to avoid them. I was actually going to... okay, let me go back 1 second. Previous. I don't have a screen here, so this is going to be fun. We're going to talk about that. But before we do that, for those of you who are not at Spike Night, we just wanted to show some of the tools we use to find problems in production, and we'll talk about how we diagnose those problems. So without further ado, I'm going to attempt... There we go. I am now connected to a workstation in our office. We're all about connecting to our workstations at this conference. Actually need to make this bigger. Oh, this will be fun. So I have a couple of the tools open. We'll burn through them. The first tool is called Perf Collector. It is written by a senior member of our operations team, Dan Farino. I just popped this guy open. This actually shows all of our web farms, and it gives us live information as to the health of that web farm. I'm going to pop open this one in particular, www main, which shows the splash page. If we're having a problem right now, you will see it. We figured out that we won't lose our jobs if we do this last night, so we're showing it right now. So this shows counters. This is a particular VIP. It has 184 servers. What you can see here is that actually a couple of the servers are having a problem, and we actually talked about that problem last night. But what you can see here is that there's a lot of servers in this farm. This farm serves our splash page. The various counters are requests per second, total CPU, errors per second, time and garbage collection, all the live data that you could possibly ask for. If you right-click on it, you'll see various tools that you can take against each server. So I'm right-clicking on one of the servers. I'll highlight it so we can see it. And if I right-click on it, I can do a stack dump. I can do a heap dump. I can pull logs. I'm not going to pull logs live because there's scary things in the logs. You can view it in Skynet, which we appropriated from an interesting movie. And so I have a couple of the tools. I'm going to go really fast, so I'm not going to do this live. I have a couple of the results of those tools open because we're going to show you those tools as we go through our diagnoses. This tool is the stack dump tool. This tool just pulled the call stacks off of one of our web servers, and it pulled it out a while back during a problem. And this shows all the threads and how long they've been blocked for and what they're blocked on. And then I can go down, hopefully. Oh, sorry. We have an issue. No. I just went to the wrong screen. There we go. Okay, this is the one I meant to look at. So this one has a particular issue, and we're going to go over that issue later. But I just wanted to show it to you. This shows all the threads running, This shows all the call stacks on those threads and what they're doing. This is a really handy. You can find probably 80% of our server-side problems using this particular tool. There are analogs to this tool out there. But over time, this tool has a lot of domain-specific knowledge about like what the request is, particular things about our code base, et cetera, et cetera. I also wanted to show a system called Perf graphs. Perf graphs collects the same information except over time. This is Perf graphs exporting www main and showing all the counters as they exist over time. And you can see the yellowed line is the average of those counters. So this graph, for example, is percent time in garbage collection over the last 24 hours. This counter tends to vary a lot, so the multicolors are individual servers varying in the midst of the counter, and then you'll see an aggregate average over there. So we're going to use a couple of these tools as we go through the system. Here's Skynet. This shows what the this view in particular shows what the net scalers are doing. This is the net scalers in front of our home VIP, which shows our home page. You can see all the servers in there. You just saw this one has a surge queue right now of 1, which is not a big deal. You see how many connections they have, average weight, etc. So we have a lot of pretty awesome tools for finding problems in production. And we'll tab out of this guy if I don't get lost in the midst of all these Windowsy things. And we will talk about how we use these tools to diagnose a couple problems, and then how we built a centralized tool that can track these problems for developers on a day-to-day basis. So not very good with the old PowerPoint. Let's keep going here. Okay, so problem 1. Looking at our performance monitors, which you just saw, there's a clear problem. Is means about 1.5 years ago. A single server stands out from the crowd. Here's a bunch of servers that are in relative states of happiness, and then you'll see a single server in the middle that has nasty, the pale brown counter is garbage collection. It has high garbage collection. Red counter is request queued against the server. Blue is high CPU. If you actually take this diagram and replicate it perhaps 100 times, you would actually see that that maybe 1 out of 30 of the servers have this particular problem. The rest of the servers are completely happy. They are happy web servers, as you can see. No red. We like to color code by badness. If you look at that individual server over time, this is a last 5 minutes view of that particular server. The blue is CPU. The brown is garbage collection. For those of you who run virtual machines that use garbage collection, this will be a familiar type of problem. So over 5 minutes, blah, blah, like everything's like fairly, not great looking because I'm a perfectionist, but it's at least running. And at a certain point, probably about 40 seconds ago, CPU shot up, went crazy. I was about to say an impolite word. And the garbage collection spat up to way higher than it did before. Oops. My skills. And queuing went up. So we have high garbage collection, high CPU, we have queuing, and then the server goes into its problem state. If we look at perf graphs over the last day, we'll actually see that this has been repeating itself. This is a graph showing the last 24 hours of garbage collection. And you'll see, this is 24 hours, so you'll see like relatively lengthy periods of time where there is a normal amount of garbage collection, and then these huge spikes, nastiness happening, bad. So in short, we have normal behavior followed by periods of high CPU, garbage collection, and queuing. And you have periods of badness, that's a technical term, occur over lengthy intervals. So now we start something that we've kind of do in the back of our heads after several years of doing this kind of thing, which is our distributed diagnosis. Distributed diagnosis is your mental checklist. Is the source of the problem on the server, or is it in the cloud, i.e. the server farms? If it's all servers and all farms evidencing a problem, network or environment issue. If it's all servers and one farm, it's a back-end problem. If it's some servers and one farm, it's intermittent server-side behavior. So in our case, because we have a couple servers out of a large farm, it's probably a server-side code issue. It is probably not a distributed problem Unless, of course, there's always exceptions to that, like a particular set of clusters had a problem, but usually not. So we think it's a single server problem. We think it's not a distributed problem. So mental checklist there. You look at a single server and you ask yourself, what is it doing? What is probably the issue? High CPU is probably looping code. High errors per second. If one server out of a bunch of servers with the same code base is throwing errors all the time, it's actually usually, in our experience, some kind of race condition. Someone had multiple threads dealing with a shared data structure, and boom, it's very easy to use static variables. And yeah, you can kill a dictionary, you can kill a map, you can kill all sorts of things with lots of threads changing it. If it's CPU plus queuing, high CPU, high queuing, it's usually blocked on I/O in which there's spin locks involved. If it's queuing without CPU, it's usually a deadlock, or once again I/O, where it's waiting on locks. We use locks to protect our connection pools, which we in turn use to protect the middle tier. If it's CPU plus garbage collection plus queuing, as in our case, it's probably the server spending a lot of time, excessive amounts of time, reclaiming allocated memory. This is the problem. Yay. So we have a memory allocation issue. What's happening on the server? So we went down a bunch of blind alleys, we dumped stacks, we looked at servers, and we saw that they all had one thing in common. Regular expressions. We love regular expressions. They're amazing for performance. They make a site run very smoothly. In this case, I'm actually not showing you the real call stack because we don't have it anymore. But I'm showing you an exemplary call stack of what it looked like at the time. The top of the stack. So we're executing through server code here, blah, blah, blah. Render children internal. This is ASP.NET stuff. And at that point, you see a method call called add soft breaks. And then you see a regular expression doing a replace, and then you see it scanning. This alone, when you see it in a call stack off of a web server, means something bad has happened. Why? Because it's very unusual to see a regular expression running for a long period of time unless you've done something very wrong. And usually when you take a call stack, you're pulling like 1 point in time off of like threads that are usually spending like 20 milliseconds doing what they do. So this is a bad scene. So all these servers had this regular expression issue in common. So we're like, okay, we have a regular expression issue. It's happening intermittently. These servers had another thing in common. We're good. Okay, we have another thing in common. Chris Crocker. Anyone recognize Chris Crocker? Leave Britney Alone. This was shortly after the Leave Britney Alone excitement, and Chris Crocker's MySpace profile was getting a lot of traffic. So what was this having to do with regular expressions? That was our fault. All of the problematic threads were executing code on the active user's viewing one of his images. That image is private, so we're not going to show it, but we're going to show what happened. This is the act of leaving a comment on an image, and you can see in this text box that someone has left the letter A repeated ad infinitum throughout the comment. So why are we running a regular expression on this? So someone is clicking submit, it's going up to the server, and yeah, single line of characters with no white space between the characters. Because you don't want to see this, blowing out the formatting, which is impossible to not blow out on certain browsers. We were chopping long lines with no white space on the server side by inserting WBR tags at intervals using this regular expression. A particular person had left a comment on one of Chris Crocker's images, which was allocating a 500 kilobyte string, and the regular expression library was recursively reallocating that library as it inserted each WBR tag after a certain interval. That was causing megabytes of memory of allocation, and the server was trying to keep itself going by reclaiming that memory, and voila, death through memory allocation. So we had a memory allocation issue. Problem number 2, login count is dropping. One day, actually you'll be able to place this time by the subject matter, we noticed a 15% decrease in requests to our login VIPs. This is not good. It means logins are going down. Well, it depends on your opinion whether or not that's good. But logins are going down. So we look at our perf graphs. Request queued is low. We want to figure out, do our distributed diagnosis, figure out if the servers are having problems. So request queue is low. Exceptions per second are low. This is good. This means we're not throwing a whole bunch of errors on the server side. Requests per second is normal. So in our login system, you go to the splash page, you log in, transitions to our login VIP, and then you go to our home page. So we look at the splash page to see if requests have gone down on the splash page. You can't tell from this graph, but you just have to believe me that they did not go down on the splash page. But they did go down on the login page. So we weren't sure what the problem was. We knew the splash page was fine, but not many people were logging in anymore. So then we hit Tom's inbox. Tom gets tens of thousands of messages per day. This is actually a very sort of useful way of getting responses from customers. And people are complaining about logging in and seeing the mouse cursor skipping over the page. Scary. Client-side issue. Yes? So we actually wanted to show you what this was. So I'll click Escape. I'll head over to this guy. Yeah, that guy. Wait, where's our orchestration? There we go. This is one of the wonderful things that we do on MySpace. So this was an ad that we ran on the splash page when you can all gasp in terror, and well, not terror, because you don't have to deal with it. But this is an ad we ran on the splash page when The Dark Knight came out. Check out CPU in Internet Explorer. If you can't see it, the CPU is at 33%. Dark Knight just like blew out the CPU on the browser. And this is a fairly beefy computer, in spite of the mouse problem yesterday. And if you're on a regular mom and pop computer, this had pegged the CPU. You have one core, you have like a Pentium 4 or something. This ad pegged the CPU and allocated 250 megabytes of RAM. These flickering images that you see are actually transparencies embedded in the flash image over and over and over that are shifting in and out using the 3D engine or something. Not really a flash guy. Either way, they conspired to cause nastiness in Flash. Poor Flash, poor us. So, what? How,
Exist at that time.
Yeah, at this time we did not have actually an automated way of monitoring the stream of ads that come through the system. That's actually still a problem in the sense that we get them from a lot of vendors, but this one we should have caught. We would be very happy if we could say that we caught this problem before, but we didn't. We simply weren't making those checks at the time. We had guidelines, and this broke the guidelines, but we didn't make those checks. So that was a particular problem, so I'll say from current slide, move on. So yeah, that was a client-side issue. Pure browser performance issue involving both CPU and memory allocation via flash. Problem 3, servers are queuing. Jeremy Custenborder is going to do this one.
Hi, everybody. I'm Jeremy Custenborder. We have a similar issue where servers are queuing across the farm. And when we say queuing, we are saying that requests are coming into the ASP.NET pipeline faster than they're going out. And we monitor this by just a standard performance counter that's built into Windows. The perf mons that we showed earlier are just a wrapper around the standard perf counters that are built into Windows. And we have that giant system to aggregate those because we just can't scale Windows RPC enough, so we came up with our own RPC layer. Now, every time we have a problem like this, we go ahead and we run through similar logic. Is it an individual server problem or is it across all the farms? Is it isolated? Is this site-wide, which is our nightmare? And then in cases when it's site-wide, you'll have all kinds of different perf monitors like this that look like this. This is not a pretty picture, and this is a very annoying thing to run into. And then on a slight tangent, a long time ago when Vista was just coming out, all of our executives decided to install it. And I thought, you know what would be cool? A Vista sidebar gadget. This is the dumbest thing I've ever done in my life because Our executives were able to figure out there was a problem with the farm faster than our monitoring solutions could. And so they're at your desk within a minute, and they travel in packs. So the way we diagnose this, let's see here. Excuse me, I'm not a PowerPoint guy. So like we said, we showed this again. This stack dump tool is absolutely invaluable. And so here's a case where it was broken across the entire farm. And this is a normal running thread. As you can see, it says it's running. It's not blocked on anything. Another running thread. But right here, we've got one that's blocked on I/O. And so we're able to go through here, and you'll see, here's the database, male federated 74. So what this says is that this particular thread was blocked for 9 seconds. That's death in our environment. Anything over a couple hundred milliseconds is death in our environment. So let me pop back over here. We diagnose most of these problems by looking at tools like the stack dump tool, looking at things like the memory allocations and the percent time in garbage collections, as well as the bytes allocated per second. And the problem in this case is that the web service thread pool was just saturated with I/O calls, so it's not doing anything. All the calls are queuing up, and we wanted to look at how we could prevent this. So I'm going to go transfer back over to Chris here.
Okay. So, yeah, 3 scenarios. I'm sure you guys can... 2? Oh, that said 4. 4, cool.
You want to go ahead and skip ahead?
So in the end, we had 3 problems. I'm sure you guys can think of 500 other problems. The thing that tied these problems together were that they caused interruption for end users, which is not acceptable. They caused slowdown for end users, which is not acceptable. And all 3 of those problems were highly preventable. Sure, in operations, we have problems that are very, very difficult to prevent. It's difficult to prevent over the course of years from having spanning tree issues or what have you. But these involve someone making a decision in their code that caused a problem that affected millions of people. So to track these types of issues, because here our goal is, can we give our developers a picture of what change is happening in production, or what change will happen in production when they develop their code. So we developed a particular system called Perf Tracker. I'm going to burn through this guy. This will not use Elmo, by Elmo. Perf Tracker is a build plugin. So you got developer commits code to source control, build system picks it up. We have a web server with a bunch of profiling stuff installed on it. We have a performance tracker. That's the actual system. The build system pushes code into the web server. Build system tells Perf Tracker to start testing. This happens once every 24 hours. It happens at night. It stores the results in a data store, which then gives a UI to developers. That's Perf Tracker. We're actually going to demo it right now. At great difficulty and a lot of fun, we actually transferred the entire ecosystem of Perf Tracker onto this laptop. So if you see a service interruption, please forgive us. So here, you want to drive it, Yadid, and I'll demo. Is it open? This is Yadid, developer of MS Fast, which we released yesterday. Okay, so the fun part of this tool is that it's an example of how you can automate something like MS Fast to give people results on a regular basis. So this tool, in the back end, this tool is run against the build on a regular basis. And what it does is it tries to give a roll-up of the types of metrics on a day-to-day basis in such a way that we can analyze change over time. Because in a system like this, small changes can mean a lot, or small changes can mean very little. So this page is a roll-up of a whole bunch of different tests that we do. On the left, you'll see like Splash, photo albums, profiles, browse, messaging, etc. And if I pop these guys open, you'll see particular tests that are run on a regular basis. We try to target the pages with the most traffic because this is a performance tool. So, and we only have so many resources. So I'm going to click on Splash. We close the dark night. Yeah, oh yeah, okay. Excuse me while I cough. So this is the results for the splash page. So this is data that we keep forever on a day-to-day basis for the splash page. And it tracks every night both client-side and server-side performance. So each one of these rows is a particular test run. So you'll see this is Splash. The iteration date, this was a couple months ago, 4609. The Splash page allocated this much memory on the web server. It made these many database calls, this many outbound HTTP calls, this many data relay calls. So these are server-side metrics. And then it gathers client-side metrics, total page weight, how large everything is, total JavaScript downloads, average CPU time on the browser, dark night, allocated browser working set. So, and then you get a page grade as well, because we run a bunch of validations against the page. And there's also, hopefully I can click this, yes. There's a bunch of other things we track as well that we don't show by default. User time, CPU time, working set, render time, etc. So that's the surface level results. And then if you click deeper into the results, here's one iteration against the splash page. And so this uses the UI of MSFast to track the actual the rendering cycles of the page. So this is a Flash-based version of MSFast. Well, actually MSFast uses Flash, but this is the not browser plugin version. And so you'll see this is the splash page as it rendered. These are all the dependencies. This is the amount of browser CPU that the page took up. And these are the regions of HTML and screenshots of what the page looked like as each region rendered. I have to wrap up. Yeah, sorry. Okay, so I'll burn through that. And then you can see actually the segments that rendered. Look at the MSFast talk because that's what MSFast does. And then you see server-side results as well. You see all the memory that was allocated for different objects, bytes at request start and end, difference, et cetera, outbound HTTP calls, and you see a call stack view of all of the middle tier calls that were made at a particular time on the page. So basically everything we need to know, sorry, burning through this part, everything you need to know in order to have avoided those three problems as they happened in production. And then what we can do with this data, this is just one way on the UI of surfacing this data. What we can really do on a regular basis is run analytics against this database and look for statistical variations. For example, if the splash page makes 0 database calls, which is a good thing because you don't want your splash page to have middle tier dependencies, then the transition from 0 to 1, i.e. a developer checked in a database call against the splash page, that could and would end up being a disaster in production eventually. So that is a variation that we track in the system so that we can notify people of what went wrong. So anyway, any questions? Okay, people can come up for questions. Apologies for going over. Thank you very much for your patience. Enjoy.